we will talk about normalization. Normalization was invented and deployed to support the relational data model and relational databases. That was quite a few years ago, but today, normalization is applied to whatever database we are designing, whether it's a relational database or a NoSQL database. Here are the goals when we do normalization. Simply speaking, after the normalization process, we want to create a set of suitable entities. Remember, we will create a model, right? An entity relationship diagram. When we design a database, we have a model, a diagram, and we want to make sure in the model, we have a suitable set of entities that can support the data requirements of a company. To be more specific, when we do normalization, we want to minimize the redundant data and pay attention to the keyword. The keyword is minimize. There is no way that we can totally eliminate the redundant data because very often we need to relate data to other data, right? In a relational data model, we have the concept of the primary key and the foreign key, the relationships. Relationships exist in the NoSQL database data as well. Therefore, we will try to minimize the redundant data, but the redundant data will exist. It's required. We will also increase the usability of our data. Think about reporting. If we have a full address in our database, a full address consists of the street number, city, state, country, and so on and so forth. And if we do normalization, we will break up a full address into atomic components such as street number, city, state. But before normalization, we will have a full address. You have your complete address in one attribute, in one column. And might look intuitive, might be convenient to have a full address, but if you want to look up people living in a specific state, for example, Massachusetts or Washington, right? You are going to look for MA or WA. So you will need to do a wildcard search. And those are very common, very popular phrases. Therefore, you will probably get a lot of false hits. So that will reduce the usability of your data. On the other hand, if we have a state column, MA for Massachusetts, WA for Washington, then it's a lot more convenient. We can precisely retrieve people living in a specific state. So that's what we meant by we'll increase the data usability and provide reporting flexibility. Also, we want to maintain the data integrity. If we want to maintain the data integrity, it's critical that we minimize the redundant data. Think about the situation this way. If you have 5 occurrences of a last name in your database, so last name exists at 5 different places in your database. If a customer calls in wanting to change the name, the last name, then you will need to update all of those 5 different places, all 5 occurrences of the last name. If we miss out one, then the data is out of sync. We have data consistency issues, right? But if we do normalization, we will minimize the redundant data. Therefore, we can maintain the data consistency. I sent out an announcement about some video assignments. One of the videos was the database development lifecycle, and there are 3 different stages for designing a database, whether we are designing a relational database or a NoSQL database. Those stages are conceptual, logical, and physical. We are going to do normalization at the logical stage. And I want to stop here to ask the class, does anyone have any question or any comment on the video that I shared a few days ago, the database development lifecycle? Any question, any comment? Okay, so a very quick review. At the conceptual design stage, our focus is to identify the data requirements. We will identify the data we need to store in the database. We are not that much concerned about the model or the platform, okay? Our focus is on the data requirements. We will also create our initial entity relationship diagram at the end of the conceptual design stage. Once we have enough details about the data requirements, we have our initial model, we will move on to the logical design stage. At the logical design stage, our focus is to select a data model. If we are going to design or we are designing a relational database, obviously we have to use the relational data model, but there are some other data models available for NoSQL databases, right? So at this stage, we will select a data model. Once we have selected the data model, we will work out more details about our design. And the details will be specific to the model we have selected. And we have more details, then we will move on to the physical stage. At the physical stage, our priority is to select a platform. Where do you want to implement your design? On what platform you want to implement your design? For our course, we use SQL Server. So I'm the boss. I have made the decision for you for the project, but there are some other choices, right? So you will want to select a platform that you are going to implement your design on. Then we will fine-tune, optimize our model, our design to take advantage of the features, specific features provided or offered by the platform. Those details are usually data types and indexing and some other things. Okay, so those are the 3 stages for the database design process. And keep in mind, normalization is a very important activity when we do database design, and we do normalization at the logical design stage. Last week, we went over data modeling, right? Data modeling is about gathering the business requirements. Therefore, usually we do data modeling at the conceptual stage. And I strongly encourage you to watch my database development life cycle, that video. It's just about 11, 12 minutes long. It's a very, very good video. It has been very well accepted. And if you have not watched it, please do it, okay? You will pick up more details related to database design. And in the data world, especially when we do normalization, there is a very important concept, functional dependency. You know, I like to explain theories and concepts in plain English, whenever it's possible. So I will try to give you a very mundane explanation or definition for functional dependency. You can also read your Carnegie and Beck book about a more formal, more detailed definition for functional dependency. My definition for functional dependency is give one, get one. Okay, I give you one requirement, you will retrieve one thing. So give one, get one. And let's look at this example. We have a very simple entity about employees. We have employee ID and employee name, just two attributes. We say employee ID functionally determines employee name. Remember my definition, give one, get one, right? You give 101, you get John. You give 102, you get Sarah. Okay, you give 104, you still get John, that's fine. You give one, get one. On the other hand, we say employee name does not functionally determine the employee ID. And think about my definition, give one, get one, right? You give John, you will get 104 and 101. So that's what we meant by employee name does not functionally determine the employee ID. Functional dependency is widely used in the data world when we identify keys and when we do normalization. Okay, here comes a good one. And I took this from your Carnegie and Beck book. Make sure you follow our discussion here as closely as possible. There are two very important properties the normalization process is based on. Those two properties are lossless join and dependency preservation. Lossless join and dependency preservation. In your Carnegie and Beck book, there are many, many pages describing these two properties and proofs, diagrams, algorithms related to these two properties. These two properties are so important because they prove the normalization process is solid and sound. Okay, I will not go over the details about proving something or the algorithm or the diagrams. Those details can be best picked up by reading the book. So make sure you do your reading assignment. Here, I just want to talk about these two properties at a relatively high level and make sure we clearly understand what these two properties are. And before we dive into the definition for each, let's look at some terms. And you can see two important properties of decomposition. Decomposition. Okay, so let me ask the class, what does decomposition mean? Do we have a volunteer? What does it mean in English?
Breaking it down into smaller components.
Excellent. And probably we are more familiar with the opposite term, right? Composition. We are probably all more familiar with composition. So to create something, right? To take pieces to make it something. So that's composition. Decomposition is the opposite. We will break up a large thing into smaller things. And also, you look at this slide, you see relation, right? We went over this briefly. Relation is entity. And once a design is implemented, we have a database, then we call a relation a table. But at the design stage, we say we have an entity, we have a relation. Okay, so those are just terms, different terms. Now we are ready to talk about these two very important properties, and I want to go over the definition. Lossless join simply means if we do normalization properly, correctly, then we can always recreate the original large entities by using the normalized smaller entities. Okay, so lossless join, lossless meaning we're not going to lose anything, right? We're not going to lose any data. The normalization process is decomposition. We are going to break down things, but if we do it accurately, correctly, then we are not going to lose any data. For example, before we do normalization, we may have 5 large entities. Then we go through the normalization process. We go through the decomposition process. At the end of the normalization process, we may end up having 10. Okay, we went from 5 large entities, 5 large relations to 10 smaller entities or 10 smaller relations. But we're not going to lose any data. We can always reconstruct the original large entities by using the normalized smaller entities. That's what the lossless join is about. The other property is dependency preservation. So dependency preservation simply means if we have business rules and business requirements that we need to implement, we need to apply, we need to enforce on the original large entities, then after normalization, we can apply similar business rules to apply the business requirements to the design to make sure the business rules will be implemented and enforced, and our data will not be compromised. So that's what dependency preservation is all about. Again, the two very important properties are lossless join and dependency preservation. Lossless join simply means if we do normalization properly, then even we break up large entities into smaller entities, we're not going to lose any data because we can always reconstruct large entities from the normalized smaller entities. Dependency preservation simply means if we do normalization correctly, then our data will not be compromised, because whatever business rules, business requirements we need to apply to those large entities can be implemented and enforced by applying similar rules to the normalized smaller entities. So there will be no compromised data. And when we do normalization in industry, we will just apply techniques which are based on these two very important properties. But if you want to go on, maybe to work on a more advanced degree, and you want to dive into database design, then you will want to pay more attention to what's covered in the Carnegie and Beck book, the theories, the concepts, the proofs, right? Otherwise, when we go out to do work in industry, we will just assume these two properties have been thoroughly researched, thoroughly proved, and we can just assume they are sound, they are correct, and all other techniques which are based on these two properties are also solid and sound. And I want to stop here to let the class digest what we just went over and see whether anyone has a question or you want to share a comment. Just a few seconds. Questions, comments? Okay, feel free to jump in anytime. And this is a holistic view of the normalization process. Before we start the normalization process, we already have a model, right? Remember, we created our initial model at the end of the conceptual stage. So our initial model before normalization is called on normalized form. So when we do normalization, we will start with UNF on normalized form. Then we will go through the normalization process step by step. We need to normalize our design to the first normal form, then the second normal form, the third, and so on and so forth. It's very, very important. We keep this in mind. There is no skipping. There's no skipping, okay? We have to normalize our design to the first before we can go to the second. You cannot say, okay, I'm so smart, I'm so experienced, I'm so skilled. I will just normalize directly from UNF to the third because I've done so much of database design. I don't need to do it step by step. No, cannot do that. Okay, keep in mind, it's very, very important. We do it step by step. And we are going to see why this is so important. And in industry, usually we normalize to the third normal form. So on your project, you will normalize only up to the third normal form. Unless we have unique and specific requirements which require more rigor then we will normalize beyond the third. Generally speaking, if we normalize to the third normal form, we will avoid almost all common data integrity issues that we may run across in industry. So simply speaking, if we normalize to the third normal form, it's good enough because almost all potential possible data integrity issues will be eliminated or will be avoided. Again, unless we have specific requirements, we don't go beyond the third. That's regarding the data integrity. Another consideration is, well, I'm pretty sure in your mind, you may think, well, if I keep going, I normalize through the end until maybe, a higher normal form, the fifth or whatever. It shouldn't hurt, right? Even, we have more rigorous design, it wouldn't hurt. Theoretically speaking, even you don't need it, but you do it, it wouldn't hurt, right? But in reality, in industry, there is a downside of over normalization. So if you do normalization, which is not needed, not required, then the performance may degrade. So, I'm talking about performance, and I think performance rings the bell for probably all of us when we develop a solution, especially when we work on or develop a project in industry. Performance is always the number one consideration. You think about normalization. Normalization is decomposition, right? Normalization is about breaking up large things into smaller things. It's all about decomposition. So if we keep going through the end in our model, we will have a lot more smaller entities. When the design is implemented, we will have a lot more tables in our database. And we create the database not just to demonstrate our skills, our abilities. We design a database for storing the data required by the business, right? To meet the business requirements. So to store the data into the database, that's just the beginning. We want to make sure when we need to use the data, we can use the data in a very efficient manner. And in a relational database, when we use data, we will write SQL code. Even for most NoSQL databases, we will also write SQL code to work with data. And let me ask the class, I know that some classmates had prior SQL exposure, SQL experience. In SQL programming, if we want to get data from multiple tables to make the data usable, to meet a business requirement, what SQL command do we need to use? What do we do in SQL to get data from multiple tables? Any volunteer?
We join the tables.
Excellent. In SQL, we do SQL joins, right? We do SQL join so we can get data from multiple tables. And in a busy environment, when we have a lot of data, that's pretty common in industry, joins are resource intensive. So it takes time to process SQL joins. It takes processing resources, memory, and CPU, right? So the more joins we need to do to get the data in a usable format, the more time it will take for us to complete our work, to complete the request. And more time required, meaning slower response, right? So if we need to do more SQL joins, then performance may degrade. As I said, once we go beyond the third normal form, you can keep going. You know, if you are a perfectionist, you say, okay, I want to make sure nothing will slip through, right? You know, I want to catch everything, even any data consistency problem which can be imagined. I want to make sure, you know, I have a design which will not let anything slip through. So you keep going through the end, then you are doing something which is not really necessary. At the end, your solution may not have a good performance. So that's the reason why in industry, we normalize only up to the third normal form, because once we normalize up to the third normal form, we can avoid almost all possible or common data integrity issues. But unless we have specific requirements, we don't go beyond the third normal form. So we want to make sure we maintain the data consistency, data integrity. We also get a good performance, right? That's the reason why the third normal form. Keep this in mind. Also, at the end of the process, you see denormalization. So normalization is decomposition, denormalization, that's composition, right? The opposite. Simply speaking, once we are done with the design for almost any project that we are working on in industry, you will run some testing in a testing environment. So you will implement the design in a test environment, and you will do some testing, especially the stress testing, load testing, right? And when you do testing, if you see performance issues, then it may be a big deal. So you want to make sure you can improve the performance of your solution, of your system, because if a system is so slow, your users will not want to use it. That's a much bigger problem. So even you just normalize up to the third normal form, or maybe a higher normal form, according to certain business requirements, during the testing, you see performance issues, you have performance concerns, then you need to do something to improve the performance. Very often, the best way to do performance, very common, is to avoid the number of SQL joins that we need to do in our application, in our system, right? But there are some other issues, such as memory, network bandwidth, and those things. Assuming those are all fine, then we will need to do something about our design to improve the performance. And the most common thing to do is to reduce the number of SQL joins. So we will do denormalization, we will do composition, we will consolidate maybe two smaller entities into a large entity. We are going backward. But when we do this, We will do it conscientiously. We will do it in a controlled manner. The key word is the controlled manner. We need to know what we are doing and then how to deal with the potential problems, right? Maybe you're building something else in your solution or some other things to make sure you will not have a data consistency problem. In the meantime, you want to improve the query performance or your system or your solution performance. So that's what denormalization is all about. Okay, any question, any comment?
Just to be clear, if we increase the number of normalizations, the performance decreases, right?
Right, because we will have more tables. When the design is implemented in the database, we will have more tables. And when we use the data very often, we need to put the data in a usable format, and we need to do SQL join to put the data in a usable format. The more tables we have, the more SQL join we may need to do to respond to a request. Making sense?
Yes, Professor. Thank you.
Great. Yeah, great question. Thank you for asking this. Any other question or comment, please? Okay. Now we have covered some theories, concepts, and the basics about normalization. It's time to do it, right? A very common deficiency for a graduate course is we learn a lot about theories, concepts, but when it's time to do work in industry, sometimes we're not prepared. We don't know how we can apply what we have learned in schools to what we need to do in industry. That's the problem I had many years ago. When I was in graduate schools, the database design was one of my specialties. And in those courses, we spent a lot of time digging into the relational algebra, relational calculus, theories, concepts, and I got a very good grade. I thought I was prepared, very well prepared to do work in industry, and I was a computer science major. But when I went out to do work in industry, it's kind of embarrassing to say it. I was a little bit lost. I didn't know how I could apply relational algebra and relational calculus to designing a database. So there was a little bit of struggle. After a few years of working in industry, I have come up with some very well-defined, well-described, very simple techniques that we can follow when we design a database, whether we are designing a relational database or a NoSQL database. Those techniques are based on the theories we went over earlier. So don't get me wrong, theories, concepts, relational algebra, relational calculus, those are all very, very important. But those are basic foundations, right? You cannot just apply relational calculus to designing a database. It doesn't work like that. And I want to reiterate, it's very, very important. We read the Carnegie and Beck book, we clearly understand the theories, the concept, and we are convinced the lossless join, dependency preservation, those are all sound and correct, right? So we get the theories, the basics covered. Now, when we go out to do work in industry, we will just apply these techniques, and techniques are based on the theories and the concepts. So I will introduce several techniques to the class, and we will go over definitions, examples, and hopefully you will find these techniques to be easy to apply and the process makes sense to you. And this is the process I have been using in industry for quite a while. And I call this Simon's process. Okay, so we will go over this step by step. And when we do normalization, we will start with UNF, right? So go back to our process diagram. So we will start with UNF. Then we will go through different forms one by one and no skipping. At the end, when we do testing, if we see performance issues, we will do denormalization. Okay, keep this in mind. And here are the 4 techniques that we need to be aware of and we need to apply when we go from UNF to the first. Remove multi-valued attributes, remove composite attributes, remove repeating groups, remove many-to-many relationship. If you read your Carnegie and Beck book and many other database books used in a graduate level data or database course, usually those authors focus on only repeating groups. But there's more than just the repeating groups. Okay, so we will go over these 4 techniques one by one. First, we want to know what the issues are. Then we will find out the best way to resolve those issues. What are multi-valued attributes? What are multi-valued attributes? Do we have a volunteer to share the definition with the class?
Yes, Professor. It can be any attribute which has like multiple values. It can all be true. For example, phone number. A person can have maybe 2 or 3 phone numbers, homework or some different. This could be one example of multi-valued attributes.
Excellent. Excellent example. Thank you very much. So multi-value attributes simply mean we have multiple values stored in a single attribute. A very good example is we put several phone numbers in the phone number attribute, right? So several phone numbers in one attribute. And I also have put together one example here. We are storing the hobbies of a person. So we have person ID. For simplicity, I don't include all details. We just use person ID, and then we have hobbies a person has. For example, person ID 1, there are 3 hobbies: reading, cooking, swimming. Number 2, person ID number 2, 2 hobbies: playing card, gardening. So in this hobby attribute, we have multiple values, right? Each hobby is a value. There are some very, very active people that are active all the time, right? They may have 20 hobbies. Then we will just put 20 hobbies in this hobby attribute. And this is a problem because number one, it's hard to predict the storage use. We may have some people that are not very active. They have just one or two hobbies, and the active people may have 20 or even more than 20 hobbies. So storage use cannot be accurately forecasted. And another thing is when you look for a hobby, then you will need to search through a long string. So because in the attribute, multiple values are treated as a long string, may not be very efficient. And if you need to update a hobby name, that's even worse. So there are issues. How do we fix it? We are aware of these issues. We know this doesn't work well. How can we fix it? How can we fix a multi-valued attribute problem? What do you think?
We need to split them up and store them in different rows,
Okay.
linking to the same person ID.
Okay. So I think many of us have used spreadsheet. Spreadsheets are commonly used in industry, not just by business people, by engineers as well. We have Excel, we have Google Sheet, and some other spreadsheets. A very common design in the spreadsheet community is to have maybe one. We still have one column for person ID. Then we will have many columns for hobby, right? Hobby 1, hobby 2, hobby 3, hobby 4. We put each hobby in a column. So in a column, we have just one value. So by doing that, we will not have the multi-valued attribute. So that's a very common practice in the spreadsheet community. Is this a good fix? Okay, keep this in mind, okay? We are coming back to revisit this in a little bit. Next, if we see any composite attribute, we want to correct it. Could we have a volunteer to give us a definition for a composite attribute? What is a composite attribute?
Made up of many fields.
Something like address?
Okay, I think that those both are good. So for example, if we have a full address in an attribute, we have an address attribute, we put a full address there, then we say it's a composite value is a composite attribute. And we said that because a full address can be broken down into street number, city, state, country. So there are atomic components of a full address. A full address is composite, but it can be broken up into atomic components, atomic attributes such as city, state, right? Okay, thank you for the input, great examples. And I have some examples here. In this very simple entity, we have a design for storing personal data, person, and a person's address. So you look at person, we have a full name. Full name can be broken up into a last name and a first name, right? An address can be broken up into street number, city, state, country, zip code. Simply speaking, we have composite attributes and they need to be split into atomic attributes. How do we fix this issue?
We split them up into columns by using space as the delimiter.
Okay, so getting very close, okay? So a common fix is that, for example, person's full name can be split into first name and the last name. So we will split this column into person's first name, person's last name. So one column will become two columns. And this full address will be broken up into multiple columns. First column is, oh, I should have used attributes, right? Because at the design stage, that's the more appropriate term. So the first attribute is street number. The second attribute is city. Third attribute is state. And then last attribute is zip code. Maybe another attribute for country. So we will create multiple attributes. And each attribute will have an atomic value. A follow-up question is that, so we will break this into two attributes, this into multiple attributes. Where should we store those attributes? Should those attributes stay in the same table or same entity, or should those new attributes be moved out into a new entity? Where do we put
New entity?
New entity. Okay, so for address, if we create a new entity for address, there are some additional benefits, right? Because an address can be shared for many different purposes, and multiple people may share the same address, assuming each person has just one address. So for simplicity, usually we just keep the new attributes in the same entity. So you will keep new attributes in the same original entity. But if you have some other requirements, some other consideration, obviously we can do more, right? You can move, for example, address attributes out to create a new address entity. But simply speaking, we will just leave or store new attributes in the original entity. That's how we fix a composite attribute problem. Now, repeating groups. Repeating groups sometimes are called logically repeating groups. Could we have a volunteer to give us one example of the repeating groups?
Gender, is that a correct one?
Getting close, but not exactly. Okay, repeating groups. Logically repeating groups. So I have one example here. In this design, we store hobbies of a person. And we went over this design, right? So this design is such a good friend of spreadsheet users. Very, very common in the spreadsheet community, spreadsheet world. So we have multiple columns for hobbies. Hobby 1, hobby 2, hobby 3, hobby 4, up until maybe the maximum number of hobbies a person may have, right? Hobby 20, how about that, right? So if a person has 3 hobbies, then 3 columns will be used. If a person has 2 hobbies, the first 2 columns will be used. There are many, many attributes, but these attributes store the same data. That's the reason why we say this is a repeating group, and these are logically repeating attributes, right? Logically repeating attributes. Hobby 1, hobby 2, hobby 3, hobby 4. They store the same data. So they are logically the same. So we say this is a logically repeating group. Now we know what repeating groups are. How do we fix them? What's the best way to fix repeating groups?
Can we have a different entity?
Excellent. Create a new entity for hobbies. In the new entity, we will have just 2 attributes, person ID and hobby. If a person has 3 hobbies, like person ID number 1, then there will be 3 rows, 3 tuples, 3 rows, 3 records in the new hobby entity, right? 1 reading, 1 cooking, 1 swimming. For person 2, there will be 2 tuples, 2 records in the new hobby entity. 2 playing card, 2 gardening. Great suggestion. Thank you for the input. So we will create a new entity named hobby and move the problematic data out to the new hobby entity. Now let's go back to revisit our multi-value attribute problem. So we have multiple values in a single attribute. A very common solution to this, especially in the spreadsheet community, is to create multiple columns, right? So you will have hobby 1, hobby 2, hobby 3. If we do that, we will fix one problem, but create another. So we will turn a multi-value attribute into repeating groups. So the best way to fix this problem is to create a new happy entity, just like what we did with the repeating groups. Also, we need to apply this technique many-to-many. If we see any many-to-many relationship, when we go from UNF to the first, we need to fix it. And I have two designs on this slide. In the top design, top model, we have students, we have courses. A student may enroll in multiple courses. A course obviously may have many students in it. Therefore, there is a many-to-many relationship between students and courses. The many-to-many relationship is problematic. It's forbidden in the relational data model. We don't allow many-to-many relationships in a relational data model. And you can see issues which are created by having a many-to-many relationship. There is a lot of redundant data, right? Student names, student info, and the course info. The biggest enemy to data integrity is the redundant data. So on the project, we will not want to have any many-to-many relationship. Okay, make sure we pay attention to that. In order to correct a many-to-many relationship, we will create a new entity, and in the bottom design, we created a new entity to correct, to fix the many-to-many relationship. The new entity is enrollments, and this enrollment is an associative entity. You can read about the associative entity a lot in your Carnegie and Beck book. Simply speaking, an associative entity is used for storing relationships. Keep this in mind. This new associative entity, enrollments, is used for storing the relationships between students and the courses. And generally speaking, we will take the parent entity's PK for creating the associative entity. So we will take student ID. Okay, so when we fix the associative, when we created the associative entity to fix the many-to-many relationship, we also implemented a new attribute, student ID, to better store the data. So we will take student ID, that's the PK of students, and it's here. We did the same thing for courses. So we will take the PK of courses, that's course ID here. You will take the primary keys of the parent entities to create the associative entity. An associative entity is a weak entity, right? It does not have its own attributes for creating a primary key. It must get the attributes, the PK attributes from parent entities for creating its own primary key. So enrollment has a composite primary key consisting of course ID and the student ID. That's how we fix a many-to-many relationship. Keep this in mind. Very, very important technique. If you see a many-to-many relationship, you will want to create an associative entity to resolve the many-to-many relationship. And the associative entity is used for storing the relationships between the parent entities. And we said, usually we take the primary keys of the parent entities to create the associative entity. The question is, can an associative entity have its own attribute? You look at this example. We took the PKs from the parent entities, right? Course ID, student ID, to create this associative entity, enrollments. Can enrollments have its own attributes? What do you think?
Yes, Professor, it can.
Can you think of a good example, or maybe one example?
Uh, g- there's nothing that's currently coming to my mind, but
Okay, yeah. I think you are getting very close. We can have, for example, the term, right? Or later, maybe we can put a grade as well. So an associative entity can have its own attributes. Okay, thank you for the input. We have gone over the 4 techniques that we need to apply when we go from UNF to the first. What are those 4 techniques? So go back to review. Multi-valued, composite attributes, repeating groups, many-to-many relationship, right? Okay, keep this in mind. And we are going to do some small group exercises. Before we work on the group exercises, I want to pause here to let the class absorb what we just went over and see whether you have any question. Just a few seconds, please. So far, so good? Excellent. Okay. We are going to do some group exercises. So we have an unnormalized form here. And we want to take this UNF to the first. Just a reminder, whenever we do normalization, we will start with our initial model, right? For example, here we are taking UNF to the first, and we want to make sure each of the entities in our initial data model has a primary key, a good primary key. Okay, that's very important. So you look at this very simple UNF. It's about employees assignments, and the PK of this entity is employee ID. And we're taking this from UNF to the first. Think about these 4 techniques, right? Did you see any issue we need to address?
Yes, Professor. Initially, what we could see over here is like there's a multi-valued issue over here.
Okay, so this similar to its repeating groups, right? Here. Are we talking about here?
Yes.
Okay, excellent. Thank you. How about other classmates? Did you see anything else?
I see for the employee and it's like composite attributes because we could like split the name to first name and last name.
Excellent. So this we have a composite attribute here, and we have a repeating group here, right? So we have seen 2 issues. Indeed, there are 2 issues which we need to address: composite attribute and logically repeating attributes. Okay. How do we fix these issues?
We can create a separate entity, maybe called project
Okay.
table.
Excellent. So move this project data out to a new project entity, right?
Yes.
Excellent. Okay. How about this composite thing?
Maybe we can divide that attribute into multiple attributes.
Okay, so maybe last name, first name, but
Yes.
leave them in the original entity, right?
Yes, correct.
Okay, excellent. So you see, I could read your mind. So we did exactly what you had suggested. So in the original entity, we had 2 new attributes, first name, last name. We also created a new project entity, and we moved the project data out of the original entity to the new entity. Now, this brings up a very, very important concept and technique about normalization. Normalization is iterative and repetitive. Okay, you must repeat after me. Okay, normalization is repetitive and iterative. It means it doesn't really matter where we are in the normalization process. Whenever we make a change to our design, we make a change to our model, we must go back to the original starting point, to the very beginning of the normalization process, to make sure when we corrected some problems, we did not accidentally introduce a new problem. Okay, so I want you to repeat after me. The normalization process is repetitive and iterative. Whenever we make a change to the model, we want to go back to the very beginning of the normalization process to make sure when we corrected a problem, we did not introduce a new problem accidentally. Now, we have to go back to the very beginning of the normalization process, meaning we are going from UNF to the first again. 4 techniques, right? Do you see any issue we need to address here? Those techniques are multi-valued, composite, repeating groups, and many-to-many. We had two issues, right? We had composite, repeating groups. And you look at this design. Do we have any composite attribute, or do we have a repeating group? We don't, right? Because we corrected them. How about the other two? The other two are multi-valued. Did you see any multi-valued attribute? No, I didn't see any, right? Probably no, you didn't see any either. How about the last one, many-to-many? Did you see any many-to-many relationship? And if we have just one entity, we will not have many-to-many relationships. But if we have more than one, we need to be more conscientious about checking the many-to-many relationship, right? So we have two entities now, employees and projects. An employee may work on multiple projects. A project may have multiple employees working on it. Sounds like we have a many-to-many relationship between employees and the project. And we didn't have this problem before. We had two problems, composite and repeating groups. When we corrected those two problems, we accidentally introduced another problem, a new problem, many-to-many, right? So how do we correct this many-to-many relationship problem? How do we do it?
We could create an associated entity with employee ID and project ID.
Excellent. Okay, excellent. Thank you for the input. So we created this deployment. This is a new associative entity. Keep in mind, this associative entity stores the relationships between the two parent entities, employees and the projects, right? Okay. We just made a change. Now we need to go back to the very beginning of the normalization process again. Okay, be patient because the normalization process is iterative and repetitive. We cannot lose our patience. We cannot lose our cool. Okay, be patient. Go back to the very beginning of the normalization process. 4 techniques again. Multi-valued, composite, repeating groups, many-to-many. Did you see any of those?
No, Professor.
Excellent. I didn't see any of those issues either. Okay. So we are good. We took our design from UNF to the first. Next, we will take a design from the first to the second. Remember, it doesn't really matter how smart, how clever, how skilled we are. There is no skipping. There's no skipping. Okay, we cannot go from UNF to the third or UNF to the second, and we went over the process up to now. Probably you already got a sense about why we shouldn't skip, right? Because when we correct an issue, we might accidentally introduce another issue. So you cannot just look at what you have now and skip from UNF to the third, whatever, right? because it's a dynamic situation. Things change when we optimize, fine-tune our design, fine-tune our model. So going from the second normal form to going from the first to the second, okay? There's just one technique we need to apply. Remove partial dependencies. If we see any partial dependency, we need to remove it. First, let's learn about what a partial dependency is. In this entity, what are the primary key? What's the primary key of this entity? Or what are the primary key attributes?
Employee ID and project ID.
Okay, so this is about assignments. And this entity has a composite primary key consisting of employee ID and the project ID. Partial dependency means if you have a non-key attribute which is functionally dependent on part of the primary key, but not the entire primary key. Okay, so for this entity, there are two primary key attributes, employee ID and the project ID. We have a non-key attribute, which is employee first name. Employee first name is functionally dependent on employee ID, but not the complete primary key. So that's the so-called partial dependency. Okay, keep this in mind. And we are doing another small group exercise. We want to take this design. So this design is already at the first normal form. We want to take it from the first to the second. First, let me ask the class, what is the primary key of this design, of this entity?
Employer ID and project ID.
Excellent. And did we see any partial dependency?
I guess the employee first name.
Okay, it's here, right? Is there any other partial dependency?
Maybe the project manager last name.
And this one, right? This looks suspicious.
Yeah.
This may also look suspicious, right? Because this is about a project and project
Yes.
duration, right?
Duration, yes. 3 of them, yeah.
Okay. Okay, excellent. And indeed, we all got sharp eyes, hawk eyes. Our eyes are very sharp. Okay, we caught the issues. So we have partial dependency with first name, and these project attributes are all partially dependent on project ID. How do we fix the partial dependency problem? How do we do it?
Can we split the table up?
Okay, create a new entity, right?
Yes.
So it sounds like creating a new entity is probably, one of our best friends when we do normalization. So create a new entity and move some of the problematic data out of the original entity to the new entity, right? So we did exactly that, created a new project entity, and we moved the project data to the new entity. Now we have two entities. And what's the primary key of project?
Project ID,
Excellent. What's the primary key of employees?
employee ID.
Employee ID.
Excellent. And a trick I want to share with the class. To think about the definition for a partial dependency. You have a non-key attribute, which is functionally dependent on part of the primary key, but not the complete primary key, right? That simply means if you have an entity which does not have a composite primary key, you will not have a partial dependency problem. So for all entities which have a simple primary key, meaning there's just one attribute in the primary key, you don't need to worry about the partial dependency. Okay, so we have two entities here. They each have a simple primary key. Therefore, we don't need to worry about the partial dependency, but be patient. Okay, be patient and don't lose our cool. The normalization process is iterative and repetitive. We are going from the first to the second, but it doesn't really matter where we are in the normalization process. Whenever we make a change to our model, always, you need to repeat after me, okay? Always go back to the very beginning of the normalization process. We are going from the first to the second, but we just made a change. Therefore, we need to go back to the very beginning of the normalization process. Now we are going from UNF to the first. Going from UNF to the first, there are 4 techniques, right? Multi-valued, composite, repeating groups, many-to-many. Did you see any of those 4 issues?
The start date can be broken down into year, month, and date, I guess.
Or the start date? Yeah, I think that's a possibility, but this is mostly about the start date of a project, not the start date of an assignment. Okay, I got that. Yeah, good point. But this is about the starting date of a project.
Right now, there is no relation between projects and employees, so we need to create we need to create associate entity.
Excellent. So we have a many-to-many relationship between employees and the project, right? And we didn't have a many-to-many relationship. So when we corrected the partial dependency problem, we introduced a new problem. That's the many-to-many relationship. And we need to create a new associative entity between project and employee for storing the many-to-many relationships between the 2 parent entities. So we created this deployment and we just made a change. Go back to the very beginning of the normalization process. Again, going from UNF to the first. Multi-valued, composite, repeating groups, many-to-many. Did you see any of those issues?
No, Professor.
Excellent. So this design conforms to the first normal form. But our goal is to bring this design from the first to the second, right? So we want to reach the second normal form. Now, this design is at the first normal form. We need to go from the first to the second. Going from the first to the second, there is just one technique, partial dependency. Did you see any partial dependency in this design?
No.
Why? Why did you not see any? What made you believe there is no partial dependency?
Could the project start date be partially dependent on project ID?
Project start date. This is functionally dependent on project ID, and the project has a simple primary key, right? And by definition, all data must be functional dependent on the PK. So we have this project. This entity has just a simple primary key. Therefore, the start date is functionally dependent on project ID. I think this is fine. Okay, thank you for checking. So let's look at the entities we have in this model. Projects, we have a simple primary key, and we learned the trick, right? If you have a simple primary key, you don't need to worry about the partial dependency. And we are going from the first to the second. So we are just looking for a partial dependency. Employees have a simple primary key. Therefore, we don't need to worry about the partial dependency. Deployment, this has a composite primary key, 2 attributes in the primary key. We need to be a little bit mindful, little bit careful, right? We need to be a little bit careful because we have a composite primary key here, but in deployment, we do not have any non-key attribute. Remember, the definition for a partial dependency is you have a non-key attribute which is functionally dependent on part of the primary key. And I would add part of the composite primary key, but not the complete primary key, right? We do not have any non-key attribute in deployment, so we are fine. So simply speaking, this design conforms to the second normal form, and we are done. I'm going to pause here for a few seconds to let you digest what we just went over and see whether you may have a question or you want to share a comment. Just a few seconds. Okay, we'll continue. Third normal form. Going from the second to the third, there is just one technique. Remove transitive dependency. So we will be looking for a transitive dependency when we go from the second to the third. Let's learn about the transitive dependency. A picture tells more than 1,000 words. I'm a strong believer in that. So I drew this diagram, okay? And you can see what's the primary key of this design, of this entity.
Student ID.
Just one, right? So we have one PK attribute. All other attributes are non-key. So we have a simple primary key here, and this is the PK attribute. All other are non-PK attribute. Okay, non-PK attribute. The definition for a transitive dependency is we have a non-key attribute, which is functionally dependent on the second or another non-key attribute. Then the second non-key attribute is functionally dependent on the primary key. Okay, so look at this diagram. Hope you like my drawing. We have this non-key attribute. So this is the department head of a major. First name, last name. So first name is functionally dependent on the major because the major has a department head, right? Last name is also functionally dependent on the major. So look at each of them separately. So program director first name is functionally dependent on major, and then major, this is the second non-key attribute. Major is functionally dependent on student ID. A student has a major. Program director last name is functionally dependent on major, and then major is functionally dependent on student ID. So we have two transitive dependencies here. How do we fix a transitive dependency? How do we fix it?
We could create a separate entity as major, and which can the program director first name and last name could be related to the major, and then we can show an association between student ID and major.
Excellent. So indeed, creating a new entity and move the problematic data out to the new entity. So creating a new entity sounds like one of our best friends when we do normalization, right? And this is at the second normal form, but it does not conform to the third normal form. Did you see any transitive dependency?
Yes, similar to the last one, manager ID is dependent on employee ID.
This and the okay.
Yes.
Okay. Okay, so we have two transitive dependencies here. Okay. Excellent. Thank you for the input. Indeed. Okay. And look at a potential or possible data integrity issue if we have a transitive dependency. And you can see in this design, we have a transitive, obviously, several transitive dependencies, this and that, right? They are all functionally dependent on manager ID, and then manager ID, that's the second non-key attribute, is functionally dependent on employee ID, that's the PK. And we have transitive dependencies embedded in the data. That's like a bomb. It's a potential problem. So when we delete a student, for example, if we delete this employee 103, we would also delete 103's manager. That's a poll right K. Okay, so that's the only occurrence of poll right K that is visible. So simply speaking, if we have partial dependencies, we may have potential data integrity issues. When we delete some data, we might accidentally delete some other data which we do not want to delete. Okay, so it's a data integrity issue. And we learned to fix the problem, go to our best friend. Our best friend is creating a new entity and move the problematic data out of the original entity into the newly created entity. That's exactly what we did. We created a new manager entity. And we just made a change, go back to the very beginning of the normalization process. We need to go from UNF to the first. So 4 techniques: multi-valued, composite, repeating groups, many to many. Did you see any of those 4 issues?
No, Professor.
Excellent. Now, this design conforms to the first normal form. We need to go from the first to the second. We will be looking for the partial dependency. Did you see any partial dependency in this design?
No, Professor.
Excellent, because we don't have any composite primary key, right? So this design conforms to the second normal form. Now we are going from the second to the third. We are looking for the transitive dependency. Did you see any transitive dependency?
No, Professor.
Excellent. So we are done. Okay. And we went over normalization. This is a very complex subject, but it's also very useful, especially when we go out to do data work in industry. We went over the theories, the concepts. We also learned a lot about definitions, and we did group exercises. And I want to pause here for a few seconds to see whether you may have a question or you want to share a comment.